Good morning. So in the last class we have seen we defined metric spaces and some definitions of metric spaces, especially um, a neighborhood, limit point, open set, closed set, etc. And we also seen that every neighborhood is an open set, and every neighborhood of a limit point contains infinitely many points, and finite set is closed, and if a set is open then its complement is closed, and vice versa. So shall continue to the next set of results. So the result says so it says so let let x be a metric space let x be a metric space let x be a metric space if if collection G alpha belongs to A is any collection is any collection of open sets in X, then union G alpha belongs to A is open in X. So there are set of four results. So we shall see one by one. So it says in a matrix space, that G alpha, collection G alpha belongs to A is any collection of an open set. Now what is this alpha belongs to A? We don't know what is A. So this says this collection G alpha is an arbitrary collection. Meaning is this collection may be a finite collection or an infinite collection. We don't know what is exactly it is. So it is just an arbitrary collection. Now how many elements are there? The number of elements in A. So cardinality of A, if it is finite then this collection is finite collection, if it is infinite then this is infinite collection. So you can say it's an arbitrary collection of open sets in a matrix space X. Then it says this union of this open set is again an open set in X, now that is arbitrary union, that is arbitrary union of open sets is again an open set. Okay, it's again an open set. Okay, we shall prove this. Okay, now that means my aim is to prove that this union G alpha is open. Now to prove this is open set, we need to prove that every point of this set, that is union G alpha belongs to A. We need to prove that every point of this set is an interior point. So let's take one point. Let X belongs to union G alpha belongs to A. Now since this X is an union, this implies that X belongs to G alpha for some alpha, because since an element is taken from the union, it not need to be in every set, it will be at least one set. So for example, some alpha belongs to A. Now what you know about G alpha? This collection is a collection of open set, therefore this G alpha is an open set. Now this X is an point in an open set, therefore this X is an interior point of G alpha. This X is an interior point of G alpha. Now what is the meaning of interior points? It says there exists some r greater than 0. There is a positive real number such that nr of X is contained in G alpha. NR of X is contained in G alpha. Now note that this NR of X is contained in G alpha, but G alpha is clearly contained in union G alpha, where alpha belongs to A. This therefore we got for an element in union G alpha, we got a neighborhood such that NR of X is contained in G alpha. That is, X belongs to union G alpha implies there exists an R greater than 0. There is a positive real number such that NR of X is contained in union G alpha. Therefore, this X is an interior point. This X is an interior point. Now this X belongs to union G alpha is arbitrary. So every point of union G alpha is an interior point of union G alpha. Alpha belongs to A implies this is an open set. This union is an open set in X. Therefore arbitrary union of open set is open. Arbitrary union of open set is open. Okay. Now the second statement is if collection F alpha belongs to A is any collection of closed sets in a matrix space Ex, then intersection F alpha belongs to A is closed set in X. It's closed set in X. Now again observe this collection alpha belongs to A, and we don't know what is A. So this is an arbitrary collection. It's an arbitrary collection of closed sets in X. So this arbitrary collection of closed sets, from this arbitrary collection of closed set, intersection F alpha belongs to A is closed in. That means this is arbitrary intersection of closed set is closed in X. That is arbitrary intersection of closed set. Arbitrary intersection of closed sets is closed in X. Now shall observe the proof. Now we have seen a result that if in a matrix space X, if E is open, then E complement is closed. Or also E is, that is nothing but it's an if and only if condition. E is open, E complement is closed. E complement is closed implies E is open. Or in other words, we also have if E is closed, then E complement is open. Also E complement is open implies E is closed. Now using this result, we need to prove that this arbitrary intersection of closed set is closed. So we shall prove that to prove intersection F alpha belongs to A is closed, we shall prove that union or we shall prove that intersection F alpha belongs to A complement is open. Now if this is proved, that is intersection f alpha, alpha belongs to a whole complement is open, then its complement is nothing but intersection f alpha, alpha belongs to a will be closed. Now consider intersection f alpha, alpha belongs to a complement. Now now using the properties of set theoretic property. Wait a second. Yeah, using the set theory property, this is nothing but union f alpha complement alpha belongs to a. Now observe each f alpha is a closed set. By this property, E is closed implies E complement is open. This implies this is an arbitrary union of open sets. It's an arbitrary union of open sets. Now, from the previous result, we have arbitrary union of open set is open. This implies this arbitrary union of open set is an open set. In X. Now, again, observe this set, that is intersection f alpha belongs to a complement is open in X. Therefore again using this result, we get intersection f alpha belongs to a complement whole complement, that is that thing, but intersection f alpha belongs to a is closed in X. This gives arbitrary intersection of closed set is closed in X. Arbitrary intersection of closed set is closed set in X. Okay, moving further. The next result is there's a third one. If collection G1, G2, so on up to Gn is any finite collection of open set in X, then intersection Gi is equal to 1 to n is open in X. That is, this says now G1, G2, Gn. This means this is a finite collection. It's a finite collection of open set. Then this is a intersection is finite intersection. So it's a finite intersection is open in X. That's this result. In short, it says finite intersection of open sets is open in X. Finite intersection of open sets in X is open in X. We shall observe the proof. Okay, now given that each Gi is open set, we need to prove that this intersection is open. That is, intersection Gi I is equal to 1 to n, it is open. Now, to prove this is open, we need to prove that every point of this intersection is an interior point. So let's take a point. Let X belongs to intersection Gi. I is from 1 to n. Now, this implies X belongs to Gi for all I between 1 and n. Now X belongs to Gi and each Gi is an open set. Therefore, for this X in Gi, there exists Ri greater than 0. Now why this Ri? Because for each I, for G1 and X belongs to G1, there exists R1 greater than 0, such that NR1 contained in NR1 of X is contained in G1. Moreover, when for x belongs to G2, there exists R2 greater than 0 such that NR2 of x is contained in G2. In general, for x belongs to Gi, there exists Ri greater than 0 such that Nri of x is contained in Gi, and this is true for all I between 1 and n. Now, observe. Okay, now choose delta is equal to minimum of R1, R2, so on up to Rn. That is, n positive real numbers existed in this set. We are taking delta as a minimum of this set. Now, my claim is n delta of x will contained in intersection Gi, I is equal to 1 to n. So take to prove a set is contained in this, consider an element. Let y belongs to n delta of x. This implies distance between x comma y is less than delta. Now this delta is a minimum of each Ri, so this delta is less than or equal to Ri for all I between 1 and n. This implies distance between x and y is less than or equal to Ri for all I between 1 and n. This implies y belongs to nri of x for all I between 1 and n. But we know that each nri of x is contained in Gi. This implies y belongs to nri of x is contained in Gi. This is true for all I between 1 and n. Now, since nr of x is contained in nri of x is contained in each Gi, we get nri of x is contained in intersection Gi. I is from 1 to n, and this y belongs to nri of x implies y belongs to intersection Gi. I is from 1 to n. Now this implies my claim holds, that is n delta of y, n delta of x, clearly contained in intersection Gi, I from 1 to n. Now this leads that for an arbitrary element in the intersection, there exists a neighborhood delta such that n delta of x is contained in the intersection. Therefore every point of the set is an interior point. Hence this set is an open set in x. Thus we proved that finite intersection of open set is open in x. Okay, moving further, the next one is the fourth result is if collection f1, f2, so on up to fn is any collection of closure sets in x, is a finite collection, is a finite collection, so if even f1, f2, so on to fn is any finite collection of closure sets in x, then union fi I is from 1 to n is closed in x. That is, given a finite collection of closed sets, its union, that is finite union of closed set, is closed. That is finite union of closed sets is closed in any metric space X. So we shall prove this now. That is to prove that union fi I is from 1 to n is to prove union fi I is from 1 to n is closed in X. It is enough to prove that its complement, that is union fi I is from 1 to n whole complement is open in X open in. Now consider union Fi, I is from 1 to n whole complement. Now this is equal to intersection Fi complement, I is from 1 to n. Now since each Fi is closed set, since each Fi is a closed set, its complement is open. So this is a finite intersection. It's a finite intersection of open sets. Now we have seen finite intersection of open set is open. Finite intersection of open set is open. This implies this set is open set in X. So union Fi, I ranges from 1 to n, complement is open set, implies union Fi, I ranges from 1 to n is closed set in X. Therefore finite in union of closed set is closed set in X. So shall recall the four result. The first one says arbitrary union of open set is open. The second one says arbitrary intersection of closed set is closed. The next one says finite intersection of open set is open. The next one says finite union of open set finite union of closed set is closed in X. Now why in the last two result? In the first two result we have arbitrary union and arbitrary intersection, but in the second, that's in 2 and 3, we have finite intersection and finite union. In the place of in the third and fourth one, we have finite intersection of open set and finite union of closed set. Why it is not arbitrary union? Why it is not arbitrary intersection of open set? Why it is not arbitrary union of closed set? Okay, so this finite condition cannot be omitted. It cannot be omitted. So we shall have some examples. Okay, so consider 1 minus 1 by n comma 1 by interval minus, for an n belongs to n, consider the interval minus 1 by n comma 1 by n. Now this interval for a natural number n, this interval clearly it's an open interval. It's an open interval, hence an open set. Open interval, hence an open set. Now let's take gn is equal to minus 1 by n comma 1 by n for all n belongs to n. So now collection gn, n is equal to 1 to infinity, is an infinite collection of open set. Now what is intersection of this gn? That is intersection gn, n is equal to 1 to infinity. That is nothing but intersection minus 1 by n comma 1 by n, where n ranges from 1 to infinity. Now my claim is okay. Before that, now observe. In each of this interval, minus 1 by n is less than 0. It's always less than 1 by n for all n belongs to n. Therefore 0 belongs to intersection. In particular, it belongs to the interval minus 1 by n comma 1 by n. In particular, it belongs to intersection minus 1 by n comma 1 by n when ranges from 1 to infinity. Therefore singleton set 0 is clearly contained in intersection minus 1 by n comma 1 by n ranges from 1 to infinity. Now let x belongs to minus 1 by n comma 1 by n intersection n ranges from 1 to infinity. This implies x belongs to minus 1 by open interval minus 1 by n comma 1 by n, where n belongs to n, and this is true for all n belongs to n. Now this implies minus 1 by n is less than x, which is less than 1 by n for all n belongs to n, for all n belongs to n. Now the first observation says singleton set 0 is contained in this set, or 0 is an element of this intersection. 0 is an element of this intersection. 0 is one element of this intersection. So the possibility that this choice of x can be 0. Suppose it is not equal to 0. Suppose this x is not equal to 0. Now, so x is not equal to 0 implies 1 by x is clearly belongs to R. Yes. Now 1 is a real number such that 1 greater than 0. Yes. Now use Archimedean property for this 1 by x and 1 using Archimedean property. There exists a natural number n, say let's take it as m, natural number m belongs to n such that m into 1 is greater than 1 by x, that is m is greater than 1 by x. In short, otherwise that is 1 by m is less than x, that is x is less than 1 by n for an m belongs to n. But what we have x is less than 1 by n for every natural number, but we here have x is less than 1 by n for all n belongs to n, but here we got a natural number such that 1 by n is less than x. It's a contradiction. Therefore x not equal to 0 is not possible. Therefore x must be equal to 0. This says the this intersection contains only singleton set 0. That is we have intersection of minus 1 by open interval minus 1 by n comma 1 by n, where n ranges from 1 to infinity. It contains only singleton set 0. Moreover, the set is equal to singleton set 0. Now observe, this singleton set 0 is a closed set. In R. Yes, we know that finite sets are closed. Therefore, this singleton set is a closed set in R. But what about the intersection? We got arbitrary intersection, or in particularly infinite intersection of open interval, or infinite intersection of open set. Infinite intersection of open set is a closed set. So that's why we are restricting to that finite intersection of open set is open. This result is not true in the case of infinite intersection, and this one is the example. Yes. Now for the second one, that is finite intersection of finite union of closed set. Okay. What happens if I take the countable union of closed set? Now, okay, for that, one second. Okay, now consider the open interval 0, 1 minus 1 by n. Consider the closed interval 0, 1 minus 1 by n for an n belongs to n. Now clearly observe, this is a closed set, or it's a closed interval, and it's a closed interval, hence it's a closed set. In R. It's a closed set in R for every n. So for all n belongs to n, this is the closed set. Let's take it as Fn. Now Fn is a closed set in R. closed set in R. Now let's observe what is union Fn when n ranges from 1 to infinity. That is infinite countable union of closed set. Countable union of closed set. So we have a countable collection of closed sets here. Let's observe what is its union. What is its union? Now take, let's x belongs to, now let x belongs to union Fn, that is nothing but union 0 closed interval 0 comma 1 minus 1 by n when n ranges from 1 to infinity. This implies x belongs to the closed interval 1 minus 1 by n for some n belongs to n. Now this implies 0 is less than or equal to x, which is less than or equal to 1 minus 1 by n, but this 1 minus 1 by n is always less than 1. So this implies x belongs to half open interval 0 comma 0 is included, 1 is not included here, 1 is not included. Okay, 0 comma 1, half open interval 0 comma 1. So now this x belongs to this set is arbitrary, so we can say that union closed interval 0 comma 1 minus 1 by n when n ranges from 1 to infinity, it is clearly contained in half open interval 0 comma 1. Now let x belongs to half open interval 0 comma 1. This implies 0 is less than or equal to x, but it is strictly less than 1. Now x is less than 1 implies 1 minus x is greater than 0. Now 1 is a real number. Now applying again Archimedean property, again using Archimedean property, there exists a natural number, say n belongs to n, such that yes, 1 minus x into n is greater than 1. Now rearranging, we get 1 minus x is greater than 1 by n, or 1 minus 1 by n is greater than x, that is x is less than 1 minus 1 by n. Now clearly this x is greater than or equal to 0, therefore this implies x belongs to union of closed interval, that is this implies x belongs to closed interval 0 comma 1 minus 1 by n, closed interval 0 comma 1 by n. Hence this implies x belongs to union of 0 comma 1 minus 1 by n, where n ranges from 1 to infinity, and that is nothing but union of fn, n is equal to 1 to infinity. Thus we got for every element in the half open interval 0 comma 1, that element is also in the union. Therefore my union closed interval 0 comma 1 minus 1 by n as n ranges from 1 to infinity is equal to half open interval 0 comma 1. Now observe we have this side, we have countable intersection of closed set, and it says this is equal to half open interval 0 comma 1. Now observe, this set is clearly not closed, it is not closed. Therefore arbitrary union of closed set need not be closed. Therefore in the definition we says finite union of closed set is closed. In the case of arbitrary, we got an example that arbitrary union of closed set is not closed. Hence this result. Thank you.